This is a presentation of a thesis proposal on methods for estimating and improving robustness of language models. While the large language models are very good in modeling problems with representative training set, they experience significant accuracy drop when exposed to a domain shift, where the origin of data is systematically adjusted. One of such cases can be a shift of time that leads to a significant change in the terminology of the shared tasks. Humans show that extrapolating this kind of shift is easy, but require the estimator to model invariant features of the problem, such as the knowledge that the cars are machines able to transport people. Currently, our models are not motivated to model such features, as the training loss can be reduced by simpler relations. Still, some models are more robust to a given shift than the others. Given a small validation set of the target domain, the robustness to a given shift can be measured. But these measures are merely point-wise estimates of the model robustness and cannot be extrapolated to different shifts. Robustness estimation is not the only case where we rely on point-wise estimates of the bigger phenomenon of our interest. Consider the term of language understanding. We agree that BERT model has better level of language understanding than fast text because it performs better on benchmarks such as glue. If the data of our application originate in the same distribution as glue, our benchmark is representative. However, in practice this is rarely the case, and we need to think about how representative our benchmark is for our task, and in case of doubts, how to pick the best model for our use case. The so-called generalization measures based on the model properties aim to circumvent the problem of benchmark representativeness. A quality of such metric can be measured by its correlation to the performance drops of the inspected model. Traditionally, such measures were bound to the expressiveness of the model, where larger models were expected to generalize worse. More recent measures are based on the model representation consistency under the model or input adjustments, for instance using dropout or altering the samples without changing their class. Other measures observe the variance of activations or gradients of the neural model. Understandably, we wonder how can such measures be useful for obtaining more robust models. The research mainly outside the NLP shows many instances of such applications, though its relation to the evaluation measures is rarely noticed. One of popular applications of the Bayesian measures, a product of experts framework, is also applied in NLP as a debiasing method. Other work uses the well-correlated measures directly in the training objectives, as regularizers or additional components of the loss. Clearly, not every model property can be formalized to a differentiable objective, though the formulation of the objective capturing the invariances of the problem is a necessary condition to model these invariances. The search for well-performing generalization measures is one of the cases where the systematic evaluation is crucial. We find examples where the two studies that differ only in the evaluation methodology can draw orthogonal conclusions. Specifically, the first study averages correlation for each measure, while the later one performs finer-grained analysis. In the result, the studies draw some exclusive conclusions on the measure's quality and applicability on the norm-based and spectral measure. Similarly, in NLP, the studies of some authors find benefits of elimination of specific data bias, for instance, for natural language inference task. Consequently, other studies find that addressing a single bias can actually cause side effects, eliminating the address bias, but biasing the model in a different way. Following studies propose that this problem can be mitigated in addressing multiple biases concurrently. Inevitably, though, the question raised is, how many and which biases do we need to evaluate for to confirm such conclusions? Enhancement of the robustness of our models is a natural incremental step towards models' ability to extrapolate training data. To make these enhancements possible, we propose to address two main directions. First, we propose to search for the invariants of the language mechanics that can be formalized into the training objectives. Some of the invariants are already addressed by the referenced generalization measures, but others might be more task or language dependent. Second, to be able to sustain the progress of development towards more robust models, we propose to avoid extrapolating conclusions from the point-wise estimates and focus more on explicitly enclosing the covariates and perturbations for which our model is provably robust. Such enclosing will not only set realistic expectations, but will also clearly outline the directions that the future work can address. Thank you, and if you're interested in either of the covered topics, please get in touch or take a look at the linked paper.